In our last lecture, we have seen that the unbiasedness condition plays a very vital role in search for a good estimator. But in practice, all parametric functions do not have unbiased estimators. The parametric functions which have at least one unbiased estimator are called estimable functions. In our present lecture, first we shall discuss the idea of an estimable function. We consider some examples. Then we shall discuss the idea of linear unbiased estimator, and we shall derive the based linear unbiased estimator under the assumption of the independence. Finally, we shall make some remarks on the unbiased estimator. In this lecture, we shall consider some properties of point estimators. In any given problem of estimation, we may have a large, often an infinite class of appropriate estimators for a given parametric function, say g theta, of the unknown parameter theta. A natural question may arise: are some of many possible estimators better in some sense than others? In order to decide whether an estimator is better than the others, we need to know certain properties. One of such property is the closeness property. Let us consider two estimators, capital T1 and capital T2, for estimating a parametric function g theta of the unknown parameter theta. The estimator T1 will be called more concentrated estimator of g theta than T2 if for every epsilon greater than 0 probability under theta mod T1 minus g theta less than epsilon, this probability is greater than equals to probability under theta mod T2 minus g theta less than epsilon for all theta belongs to script theta. Let us write this equation as star. A necessary condition for star to hold is that expectation under theta T1 minus g theta whole square is less than equals to expectation under theta T2 minus g theta whole square for all theta belongs to script theta, provided expectation under theta Ti minus g theta whole square exists for all I equals to 1, 2. To prove the result, let us consider the following lemma. For any non-negative continuous random variable x whose expectation exists, expectation of x equals to integral 0 to infinity probability capital X greater than small x dx. Since T1 minus g theta whole square is a non-negative random variable, expectation T1 minus g theta whole square equals to integral 0 to infinity probability under theta mod T1 minus g theta greater than epsilon d epsilon. Therefore, expectation T1 minus g whole square will be less than expectation T2 minus g whole square if probability under theta mod T1 minus g greater than epsilon, this probability is less than equals to probability under theta mod T2 minus g greater than epsilon for all theta and for all epsilon greater than 0. That is, probability under theta mod T1 minus g less than epsilon, this probability is greater than equals to probability under theta mod T2 minus g less than epsilon for all theta and for all epsilon greater than 0. From the above result, it is clear that the closeness of an estimator t can be measured by the quantity expectation under theta t minus g whole square for all theta belongs to script theta. It is called the mean squared error or MAC of the estimator t. Thus, MAC of an estimator t for estimating g theta is defined by MAC under theta bracket t equals to expectation under theta t minus g theta whole square for all theta belongs to script theta. The term t minus g theta is called the error of t in estimating g theta, and thus expectation under theta t minus g theta whole square is called the mean squared error of t. It measures the average squared difference between the estimator t and the parameter g. Naturally, we would prefer an estimator with smaller or smallest MAC. If such an estimator exists, it will be the best for the parameter g. An estimator t is said to be best for g if it has the smallest MAC among all estimators of g, that is, MAC of t under theta is less than MAC of t dash under theta for all theta belongs to script theta for any other estimator t dash of g. The problem is that no such best estimator will exist in this sense. Let, for a particular value of theta, say theta naught, t dash be defined as t dash equals to g theta naught for all small x belongs to script x, where script x is the sample space. Then MAC of t dash under theta naught is equals to 0. Since MAC of t under theta naught is less than equals to MAC of t dash under theta naught, it follows that MAC of t under theta naught is also equals to 0. Hence, t equal to g theta naught with probability 1. Since theta naught is arbitrary for any theta, t equal to g theta with probability 1. But t being a statistic, it cannot be a function of the unknown theta. Hence, such best estimator does not exist. Let x1, x2 up to xn be IID, normal random variables, each with mean theta and variance 1, where theta is unknown. Let us consider the following two estimators of theta. One is t equals to x bar and the other is t dash equals to theta naught, where theta naught is any specific value of theta. Now, MAC of t under theta is equals to 1 by n, because x bar follows normal with mean theta and variance 1 by n, and MAC of t dash under theta is equals to theta naught minus theta whole square. Now, for values of theta belonging to the interval theta naught minus 1 by root n to theta naught plus 1 by root n, the MAC of the estimator t dash is less than the MAC of the estimator t. But for other values of theta, MAC of t dash is greater than MAC of t. Here, t dash is a freak estimator of theta, since it always estimates theta to be theta naught, and it does not depend on all observations. But t1 is a better estimator than t2 because it utilizes all the observations. From the above discussion, it is clear that if MAC is the only criterion in search for a good estimator, then there may be some freak estimators like t dash, which would perform better than a generally good estimator at some specific points. It is therefore necessary to eliminate such freak estimators in search for a good estimator. Now we define the unbiased estimator. An estimator T is said to be an unbiased estimator of g theta if expectation of t under theta is equals to g theta for all theta belongs to script theta. If t is not an unbiased estimator of g theta, then the bias of t is defined by b theta t equals to expectation of t under theta minus g theta for all theta belongs to script theta. We shall now show that the MAC of an estimator t can be decomposed into two parts. One is the variance of the estimator t and the other is the square of the bias of t. To prove the result, we see that MAC of t is equals to expectation under theta t minus g theta whole square. We can write this as expectation under theta t minus expectation of t plus expectation of t minus g theta whole square. Expanding the square term, we get expectation under theta t minus expectation of t whole square plus expectation of t minus g theta whole square plus 2 into expectation of t minus g theta into expectation of t minus expectation of t. The last term is equal to 0. Therefore, MAC of t is equals to expectation under theta t minus expectation of t whole square plus expectation of t minus g theta whole square, which is equals to variance of t plus square of the bias of t. Thus, MAC incorporates two components, one measuring the variability of the estimator, that is the precision, and the other measuring its bias, that is the accuracy. Now we shall consider some examples where the MAC of a biased estimator is smaller than that of an unbiased estimator. The first example, suppose x1, x2 up to xn are IID, normal, mu, sigma square random variables, where mu and sigma square are unknown. Consider all estimators of sigma square of the form capital T equals to some constant c into s square, where c greater than 0 and s square equals to 1 by n minus 1 into summation over I from 1 to n xi minus x bar whole square, where x bar equals to 1 by n summation over I from 1 to n xi. Now, MAC of Cs square equals to expectation Cs square minus sigma square whole square. This is equals to c square into expectation s to the power 4 minus 2c into sigma square into expectation of s square plus sigma to the power 4. Since n minus 1 into s square by sigma square follows chi square n minus 1, it follows that expectation of s square is equals to sigma square and expectation s to the power 4 is equals to n plus 1 by n minus 1 whole into sigma to the power 4. Thus we get MAC of Cs square is equals to sigma to the power 4 into c square into n plus 1 by n minus 1 minus 2c plus 1. Let us write the function as hc, which is a continuous function of c. Now differentiating hc with respect to c, we get h prime c equals to sigma to the power 4 into 2c n plus 1 by n minus 1 minus 2. Setting h prime c equals to 0, we get c equals to n minus 1 divided by n plus 1, and hence t equals to 1 by n plus 1 into summation over I from 1 to n xi minus x bar whole square. Clearly, t has the minimum MAC among all estimators of the form C into S square. But T is not unbiased for sigma square since expectation of T equals to n minus 1 by n plus 1 into sigma square. Hence, T is a biased estimator of sigma square having smaller MAC than the unbiased estimator S square of sigma square. Consider another example. Suppose x1, x2 up to xn be independently distributed normal theta, 1 random variables, where theta is unknown and it is known that mod theta less than equals to 1. Here x bar is unbiased for theta because x bar follows normal with mean theta and variance 1 by n. Consider the following estimator T of theta such that T equals to minus 1 if x bar less than minus 1, equals to x bar if modulus of x bar less than equals to 1, and it is equals to 1 if x bar greater than 1. Then expectation of T is equals to probability x bar greater than 1 minus probability x bar less than minus 1 plus integral minus 1 to plus 1 x bar into f x bar dx bar. Clearly, expectation of T is not equals to theta and T is a biased estimator of theta. But MAC of x bar minus MAC of T is equals to integration minus infinity to plus infinity x bar minus theta whole square f x bar dx bar minus MAC of T, which is equals to integration minus infinity to minus 1 x bar minus theta whole square minus 1 minus theta whole square into fx bar dx bar plus integral 1 to infinity x bar minus theta whole square minus 1 minus theta whole square into fx bar dx bar. Now in the first integral, x bar less than minus 1 implying x bar minus theta less than minus 1 minus theta less than 0. Therefore, x bar minus theta whole square greater than minus 1 minus theta whole square. In the second integral, x bar is greater than 1 implying x bar minus theta greater than 1 minus theta greater than 0, which implies x bar minus theta whole square is greater than 1 minus theta whole square. Therefore, the difference between MAC of x bar and MAC of T is greater than equals to 0, and therefore MAC of T is less than equals to MAC of x bar. In the present lecture, we have seen that for a binomial population with parameters n and theta, where n is known, the only estimable functions of theta are polynomials in theta of degree n or less. As a result, we have seen that 1 by theta is not estimable. In the present lecture, we have also seen that an unbiased estimator may not be admissible, it may not exist, it may not be unique, and finally, it may not be invariant under a transformation. Also, we have seen that we can estimate 1 by theta by using an inverse binomial sampling scheme.